Alright fellas, I hope you're ready, because now we're going to try to find the determinant of an n by n matrix. To recap from the last video, we saw for, what's going on? We saw for a 2 by 2 matrix, we can write the determinant in 2 plus 2 equals 4 ways, right? It was, remember the AA plus B, capital B. So we're going to have 4 ways, and the determinant is actually going to have the determinant of the matrix has 4 terms. Two terms. Right? Remember for the m equals a, b, c, d, the determinant of the matrix was nothing more than ad minus bc. That's 2 terms, right? 2 terms is 2 factorial. For the 3 by 3 case, we can write the determinant in 3 plus 3 equals 6 ways, as we saw in the previous video, and this gave us this, and then we found the determinant actually has 6 terms. And if you remember, m equals a, b, c, d, e, f, g, h, I, right? And then the determinant of m was, okay, let me just do it real quick. We're going to have a, if I Laplace expand in the first row, it's going to be a times e, f, h, I, and then minus b times df, gi, and you guys should practice this too. Pick any matrix that you want, and then just try to find the determinant, and Laplace expand in the rows, the first row, second row, third column. Just keep practicing it until you're very comfortable with it, because right now I can just do it really easily. So here, this one is going to have 2 terms, this is going to have 2 terms, and this is going to have 2 terms, 6 terms total. And 6 terms, nothing more than 3 factorial. So naturally, for an n by n matrix, we can speculate that the determinant of m will have n factorial terms. Okay? And then, going a step even further, a result from probability theory, you don't have to know this, I'll just give it to you right now, this is a theorem, is that the number of permutations of n, let's say, objects, okay, so the number of permutations of n objects equals n factorial. Okay, and by permutation I just mean a permutation P is nothing more than taking like an ordered set, like 1, 2, 3, 4 all the way to n, and I'm just going to change the order of them. So this can go to like P of 1, P of 2, all the way to P of n. A permutation just changes the order. Okay, so for example 1, 2, 3, a permutation of that would be 2, 3, 1. Okay, it just takes an ordered set and changes the order. Okay, that's all it does. So the number of permutations of n objects is n factorial. If I have n numbers, it's going to be n factorial ways to change the order of them. Okay, that's just a theorem. So, why am I talking about this stupid probability theory? Well, since the determinant of m has n factorial terms, then we can speculate that the determinant of m is a sum over permutations. Is it true? Is it not true? We're about to find out. And now to generalize this, instead of doing A, B, C, D, like, we're gonna run out of letters eventually, right? This is why I've been stressing this index notation so much. Use indices. We're gonna use indices, because for the, let's say we have 2,000 dimensional case, we're not gonna write so many letters, you know? So 2 by 2 case, let's use indices now. The determinant of m is just m11, m22, minus m12, m21. Take a look at that real quick, stare at it, embrace it, and tell me it's right. Just scream it at me. It's right, isn't it? m11 is the top left, M22 bottom right. M12 and M21 are the off-diagonal terms. So this is indeed the determinant. Okay? 3 by 3 case. I'm going to write it down for you right now. Determinant of M. Okay, so it's going to be this. M11, M22, M33. And then we're going to have... Okay, I'm going to need some room here. Then we're going to have M13, M21, M32. Then we're going to have M12, M23, M31, minus M12, M21, M33, minus M11, M23, M32. Almost done here. We got 6 terms. M13, M22, M31. Woo! Okay, and the way that I did this is honestly, I just looked at, remember we had this from earlier, we had the expression AEI minus BDI, etc., right? We had that expression, so I just matched up all the, letters to its corresponding elements. So, if we take a look at this real quick, and this is right, you can double check me all you want, but this is right. If we take a look at this real quick, we got M11, M22, M33. If we take a look at this real quick, we'll notice something. Let's stare at this guy real quick. We notice that it looks something like this. We have M1 and then something times M2 and then something times M3 and then something. Right? M11, M22, M33. M1 something, M2 something, M3 something, M1 something, M2 something, M3 something, M1 something, M2 something. Okay, you get it, right? And what these are is exactly what I just talked about. These are nothing more than the 3 factorial permutations, right? Of 1, 2, 3. Wow, it's crazy, right? But there are some minus signs here. So, depending on if the permutation is even or odd, we put a plus or a minus. And what do I mean by an even and odd permutation? Well, this would be an even permutation, and this would be an odd. So the order matters in permutations. 1, 2, 3, order is conserved, it's an even permutation. 1, 3, 2, you flip 2 and 3, right? So it's not an even permutation anymore, so it's an odd permutation. So the culmination of this is that we can finally write the determinant of an M by M matrix as this. It's going to be the sum over all permutations P. It's going to be the sign of the permutation. And then we're going to have M1 times permutation of 1, M2 permutation of 2, dot dot dot, Mn permutation of n. This is the formula of the gods. And this is what everything has led up to. This formula. This is the determinant of an n by n matrix, written in terms of the permutations of the elements. Okay, you don't believe me? Okay, I wouldn't believe myself. Let's do it. We're a 2 by 2 case. The determinant of M is nothing more than the sum over the permutations, and since it's 2-dimensional, we're just going to have sine of P, right? M1, P1, M2, P2. Okay, so what are all the permutations we can have for a 2 by 2 case? Well, I said, remember from the theorem in the probability theory, we're going to have n factorial permutations. 2 factorial is nothing more than 2. So basically our permutations are 1, 2, and 2, 1. I mean, anybody can have thought of that, right? Okay, so 1, 2 is an even permutation, so it's just going to be M11, M22, notice we're putting the 1 in here and we're putting the 2 in there. And then this permutation is odd, right? So we're going to put a minus and then M1, 2, M2, 1. Would you look at that? Would you look at that? It's exactly the same as what anybody would think it is. This is the determinant of a 2 by 2 matrix. But the beauty of this expression is that this applies to an n by n matrix. We just have to find all the permutations. And this is why, this is the richness of linear algebra, the richness of it. Okay? So it looks complicated. It looks like a complicated expression, right? You have a sum over, you can have a n sums over here, but it's actually pretty simple. It's actually pretty simple. Okay? So from this, we can find out actually a lot of properties about determinants, which is what we're going to do right now. We could do it over here in the top. So properties of determinants. Properties of determinants. All right, number 1. If we multiply any row of a matrix, so this whole time I'm going to be using this matrix M. If we multiply any row of a matrix by some real number, then okay, let me write this down. If we multiply any row by some number lambda, some real number, then the determinant, which I'm just going to write as a fancy d, determinant just goes to lambda d. How can we see this? Well, okay, if we multiply any row, that just means that we're going to multiply, let's say we multiply the jth row. Okay, so the jth row will go to lambda times m, the jth row, and then the permutation of the jth row. And then in the formula for the determinant, remember, it's a multiplication of the elements. So if we have one term that's m, lambda m, then we can pull this lambda out of the sum, and it's just going to multiply the whole determinant by lambda, right? That's pretty neat. Since everything is multiplied in that formula, we can just pull this lambda out, and it's going to multiply the whole determinant by lambda. Okay, that's pretty neat. What else? What else, you might ask? Well, okay, if we switch, oopsie doopsie, if we switch, what is going on? Alright, if we switch 2 rows of the matrix, then actually the determinant flips sign. That's a neat expression. I mean, that's a neat conclusion. What's the proof of that? Okay. Well, okay, let's call the matrix where it flips M prime. So M prime is the matrix where the 2 rows are flipped. And for convenience, just arbitrarily, let's say that the first 2 rows are flipped. So then this is going to be, using our formula, it's going to be sine of the permutation, and then M prime of 1, P of 1, M prime of 2, P of 2, all the way to M prime of N, P of N. And in terms of our original matrix, right, in terms of our original matrix, is going to be M of 1, but P of 2. Because remember, we flipped the first and second row. So for the first row of the original matrix, it's going to be a permutation of the second row, because it's flipped. And similarly, for the second row, it's going to be permutations of the first row, because they're flipped. And everything else is going to stay the same. Okay, and I can write this as negative sum over sine of permutation as M1 Q of 1, M2 Q of 2, all the way to Mn Q of n. And what is Q? Q is a new permutation that I defined that's equal to Px. And x is the permutation that exchanges 1 and 2. Okay, so permutations, they follow the same convention as matrices. First you do X, which switches 1 and 2, and then you do P, which is the permutation. Okay? So Q is this new permutation that we defined. That's first X to switch the rows, and then P, the regular permutation. And since we do the switching of the rows, we have to put a minus sign there. So this is nothing more than the negative determinant of M. And that's our little proof there. Okay? So, I mean, this is kind of, first time I saw this, I didn't really believe it. So I just, as an exercise for you guys, you can do this for a 3x3 case. Alright? And see that if you actually switch the rows, then the determinant flips sign. And you'll see the real meaning of this. Because this is kind of hard to explain. Like, what does it mean to multiply a permutation with another permutation? It's kind of hard to explain, but it's much easier to see if you actually write it out. Okay? A couple more things that I want to do. So let me just save this real quick. I'll call this Deep Dive 3A. Okay? I have a couple more properties for you guys to just experiment with. Okay. Here we go. There we go. There we go. Okay. Number 3. Third property is if two rows of a matrix are identical, then the determinant is 0. Okay, that's an interesting one. What's the proof of that? Well, if we go back to 2, property 2 was that if we flip two rows, then the determinant flips sign, right? So if we flip two rows, then the determinant flips sign. But if two rows are identical, then the determinant of M must be equal to the negative determinant of M. Right? Because if two rows are identical and we flip them, they're still going to be the same thing, right? So that means that the determinant of M is equal to negative determinant of M. And the only way that this is possible is if determinant of M is equal to 0. So that's a neat little proof. One last one that I want to go over with you guys is that this is actually an important one. If we multiply any row by some number lambda, if we multiply any row by lambda and subtract it from another row, then the determinant stays the same. And if you remember from Max's videos on row reducing a matrix, this corresponds to multiplying any row by lambda and subtracting it. This corresponds to elementary row operations, right? Elementary matrix operations, elementary row operations. And why does it make the determinant stay the same? Well, the proof of this is that, let's say we just arbitrarily the third row. Okay, so this means row 3 and all the columns, column K. So we multiply the third row, we send the third row to the third row minus lambda times, let's say, I don't know, the fifth row. So we took the fifth row, we multiplied it by lambda, and we subtracted from the third row. And how does this affect the determinant? Well, the determinant goes to the formula again. It's going to be sine of p, and then we're going to have m1, p of 1, m2, p of 2, and then we're going to have m3, p of 3, minus lambda, m5, p of 3. P of 3. This is very important. It has to be p of 3 because it's the third row, right? It's the third row, so it's going to be the permutation of the third row. And then dot 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 mn p of n. Okay? And then since we have a minus sign here, we can expand this out. So it's going to be sine of p. And then I'm going to have m1, p1, m2, p2, m3, p3, all the way mnpn, right? And minus lambda times some sine of p, right? We're just expanding this guy out. That's all we're doing. So it's going to be m1, p1, m2, p2, and then we're going to have m5, p3, and then m4, p4, and then m5, p5, all the way to m and pn. Okay? And now notice what's happening here. This guy, this term right here, this guy right here, okay, this is nothing more than just a determinant of m, right? This is nothing more than the determinant. But this guy right here, notice that we have m5, p3, and m5, p5. Now what does this mean? If we really think about it, we're taking the fifth matrix, the fifth row, sorry, and taking the permutations of it, and the fifth row and taking the permutations of it. So these two are the same row. And if you remember from property number 2, I think it was, no, it was property number 3. If two rows are identical, the determinant is 0. So here, these two are identical, m5 and m5. These are both the fifth row. And since two rows are identical, it's just 0. So this is just a determinant. Okay? It's a cute little proof for you. And then one last one that I want to go over with you is that this is a pretty cool one. Everything that applies to rows, also applies to columns. Okay, so remember we were saying that if we subtract lambda times a row with another row, the determinant stays the same. We can say the same thing for columns. If we subtract lambda times the 8th column minus the 3rd column, the determinant stays the same. And as a corollary to this, what does this imply? Well, this implies that the determinant of a matrix is the same as the determinant of its transpose. Because transpose is nothing more than, as we said, transpose is nothing more than switching rows and columns. And if I just said that everything applies to rows also applies to columns, then the determinants are the same. And a little proof of this, if you're wondering, is that, well, just rotate your head. Just rotate your head 90 degrees. If you rotate your head 90 degrees, rows are going to be columns and columns are going to be rows. There's your proof. Okay, so hope you like that example. I hope you like this little determinant. I'm sure this is actually a very cool formula, and I enjoy it a lot. And every time someone asks me to do like a really complex determinant, I always whip this bad boy out, and it provides a lot of insight into the structure of determinants. So next time we're going to do a couple of examples using these little properties that we went over today, and then we're going to get to the main story, which is the inverse. How do we find the inverse? We spent all this time talking about the determinant, right? We've went really in depth into determinant. We found this formula for determinant. We know that the determinant is nothing more than a sum of permutations of the matrix elements. We found some rules for determinants. But now let's try to find the inverse. Okay? So I'll see you then.